Okay, so welcome. Welcome to the first application section in ICAPS. We have 4 interesting talks. One is the Best Paper Award for Application, and the last one is a paper from the journal Track. In the middle, we have 2 very interesting presentations. So the first talk will be given by Meghna Lowalekar, and I give you the word. Okay.
Good afternoon, everyone. I'm presenting the paper ZAC, a zone path construction approach for effective real-time ride sharing. This is a joint work with Professor Pradeep Varakantham from SMU and Professor Patrick Jaillet from MIT. Real-time taxi sharing platforms such as Uber, Pool, Liftline, and GrabShare have become hugely popular in recent years. There is also a recent increase in the popularity of on-demand shuttle services. These shuttles have fixed pickup and drop-off points, which is a small subset of complete road network of a city. There are significant benefits provided by these ride-sharing services. They allow customers with similar itineraries to share a vehicle. So this reduces the cost for customer and increases the per-trip revenue for the drivers. In addition, they also help in reducing the traffic congestion on the roads. In the real-time ride-sharing problem, at each time step, we take the current status of the vehicles. There can be different kinds of vehicles such as taxis, minivans, or minibuses, etc. There is also a set of customer requests which are available. Each request has a pickup and a drop-off location. There is a need to satisfy the quality of service constraints such as the time windows associated with pickup and drop-off of requests. For example, it is reasonable to wait for 5 minutes to get picked up using a cab, but if the wait time is around 11 minutes, the user will probably look for other options. Similarly, while sharing compared to standard route, a small detour is expected, but having a delay of more than 15-20 minutes will not satisfy the customer. The objective in these ride-sharing problems can be to maximize the revenue or to maximize the number of requests served. It can also be to minimize the overall delay. The algorithms which are designed to solve the ride-sharing problems should output an optimal assignment of vehicles to different groups of customers while satisfying the time window and the capacity constraints. In recent times, many heuristic approaches have been proposed to solve the real-time ride-sharing problem. Most existing research can be categorized into 2 types. The first category involves finding a greedy solution which assigns one request at a time to the best available vehicle. Most of these approaches are applicable for high-capacity vehicle. The other category of existing work includes finding a batch solution which assigns all active requests together in a batch to the available vehicles. Batch solution takes significantly more time to compute, but the solution quality is better than the assigning one request at a time. Most of the proposed approaches in these categories are for low-capacity vehicles. A recent work by Alonso Mero focuses on high-capacity ride-sharing for involving batch assignments. Similar to them, we also focus on this category. We refer to the Alonso Mero's approach as strip-based formulation, which constructs a request vehicle and request strip vehicle graph to compute the combination of requests. For online computation, heuristic and time limits for different steps are used. We propose a zone path construction approach which uses abstraction of locations into zones and an offline-online path generation method to generate the request combinations efficiently. We now highlight the difference between the approaches. As we discussed, for ride sharing, we need to generate different combinations which can be grouped together. In the existing approach, different request combinations of size 1, 2, and 3, etc. are generated, and the vehicles and requests are assigned to these request combinations, which are referred to as strips. On the other hand, we consider zone paths and assign request and vehicle to these zone paths. A zone path can represent multiple trips. For example, a path which serves a request 1, 2, and 3 can serve all the combinations. Therefore, it automatically captures multiple relevant trips. As an example from the data, there is a vehicle and it has different requests in its vicinity. Therefore, these requests can be combined together to form feasible trips for this particular vehicle. TBA first identifies that the 39 requests can be served using the vehicle. It then starts combining 2 requests at a time and generates 85 such combinations or trips after satisfying the time window constraints. After generating 36 combinations of 3 requests, it runs out of time and cannot generate any more trips. In total, it generates 160 trips for this particular vehicle. On the other hand, using ZAC, we generate 27 paths which can capture around 247 trips of different sizes. On looking into more detail, we obtain that we can combine up to 6 requests together while ensuring the pickup and drop-off constraints. The main challenge is to efficiently generate these zone paths in real time. We first define the zone and the zone path. A zone is an abstracted location obtained by clustering the locations in a city. A zone path is an ordered sequence of nodes where each node is either an exact location or a zone. To reiterate, the key advantages of using zone paths is that it can represent multiple trips. Moreover, we can generate them at different levels of granularity. As we have limited time available, we generate a part of the zone path offline. The time span of the path generated offline is tau, which is the pickup time window. So using these paths against incoming requests will not only tell us which requests can be picked up along the path, but will also provide a pickup order. These zone paths are then completed online based on the incoming customer requests. Therefore, online we only need to compute the drop-off order while ensuring that the delay constraints are not violated. As due to abstraction, the travel time is approximately represented, it can result in longer estimates of wait time. The psychology of waiting says that the pre-process waits are more unpleasant than the in-process wait. In the context of ride-sharing system, these pre-process waits refers to the wait for pickup and in-process wait refers to the wait time spent between pickup and drop-off. Therefore, to ensure that there is no additional delay while pickup, we due to abstraction, we generate the offline partial paths at the level of individual locations. The online path completion can use the higher level of granularity. The figure shows an example zone path. The red markers represent the offline partial path. The black circles and the red rectangles represent the zones. The decision to move from the marker F to the black zone and then to the red zone is taken online based on the available requests. Here we represent all the components of ZAC. The online at each time step, we get the incoming request and the vehicle status. Then we process them against the offline partial paths. The zone paths are then completed online and edges between the paths and requests and the paths and vehicles are identified. After that, we use an integer optimization program to make the assignment and we simulate the motion of vehicles. The process is repeated at each time step. We now show the steps of ZAC in more detail. As mentioned before, we generate all partial paths of time span tau, that is the time during which requests can be picked up. When this value is low, we can generate all possible paths using exhaustive search. But for the higher value of the waiting time, we use a data-driven approach to keep the paths which can group higher number of requests together. These offline paths are stored by indexing on location and time for quick online processing. Based on the currently available request and vehicle status, the offline partial paths are processed online. The paths are processed in parallel to speed up the computation. As an example, if these are the requests available, we process them against the offline partial paths to identify the requests which can be grouped together, based only on their pickup location. Therefore, these offline partial paths form small overlapping clusters of requests based on pickup and provide a pickup order for these requests. To complete the partial paths online, we start an exhaustive search at the end node of the path. With each drop-off location, we also store the upper limit on the time by which it should be visited, and we only explore those branches in the search tree where these time limits are satisfied. The exhaustive search complexity depends on the number of destination locations of the request grouped along the path. Therefore, we use zones while performing the exhaustive search. The trade-off between the computational complexity and the abstraction error is handled by selecting the zone sizes dynamically for each partial path. We show the online path completion in detail for one specific offline path. The green markers represent the pickup location of the request grouped along the path. The blue markers represent the drop-off location of the requests which were grouped along the path based on the pickup location. The drop-off locations are then further grouped based on the different zones. And the path is completed by starting the exhaustive search at the last green node. As mentioned before, with each drop-off location, we also have the time stored by which it should be visited, and we only explore the part of the search tree. These are the paths which are generated using the exhaustive search. Overall, if we see the complete zone path, this offline path results in generating two zone paths. The first one is represented using this red arrow, and the second completed zone path is the one which is represented by this green arrow. The next step to identify the edges in the RPV graph is executed in parallel to the previous steps, where an edge is present between the request and path if the path visits the pickup and the drop-off location of the request within the time window, and an edge is present between the vehicle and path if the initial location of the vehicle is the same as the starting location of the path, and the path visits the location of the request which are already assigned to the vehicle. Finally, to find the optimal match in the RPV graph, we use an integer program with the objective to maximize the number of requests served. The constraints in the formulation ensure that each demand element and each vehicle is assigned to exactly one path. And at each node of the path, the capacity constraints are satisfied. And at the end of the optimization formulation, similar to the existing work, we rebalance the vehicles to the high demand areas. We conduct our experiments on two real-world data sets belonging to two different cities. For each city, we take the drive network from the OpenStreetMap, that is the street network which consists of all drivable routes. From this network, we take the strongly connected component, which results in having around 4,373 nodes and 9,540 edges for the New York dataset. For the other city, we have nearly 21,000 nodes and 41,000 edges in the graph. The travel time on the edges in the network is computed using the algorithm provided in the paper mentioned, and we use the mean travel time in our experiment. We compare the service rate, that is the percentage of the total available requests served, and also the runtime to compute a single assignment. We take the average results over 1 week of. To create the zones we use two clustering methods which have been used in the similar works earlier. In the grid-based clustering, we divide the map into multiple rectangular grids, and for the other method which we use is the hierarchical agglomerative clustering. Based on our experiments, we identify that the hierarchical clustering with the mean linkage provides the right trade-off between the solution quality and the runtime. We run the algorithms on our simulator by varying different parameters, such as the number of taxis, the time of the day, and the different values for the delay constraint. This is a small video for our simulator. In this, we observe the path taken by one vehicle in the video and how the requests are picked up and dropped off along the path. And we also can compare the two algorithms and observe the difference in the service rate and the average occupancy of the vehicles. For the New York dataset, we observed that the service rate increases by nearly 2.7%, and the runtime to compute a single assignment is less than the existing approach. As our approach also uses zones, we also measure the error obtained due to abstraction. To quantify the abstraction error, we measure the percentage of requests which have delay above the allowed drop-off delay, and also the maximum delay which is obtained above the allowed value. And in all the cases, we observe that the abstraction error is minimal. All the real-world datasets do not capture all the sharing scenarios. That is where many requests can be paired together at a single time step. Therefore, we also perform an experiment on the synthetic dataset which can represent the on-demand shuttle service scenario. This dataset is taken from a paper by Bert Simmons. This street network has 192 nodes and 640 edges. There is one downtown area in the middle, and there are 8 suburbs, and we create a train station at one node of each suburb, which is marked with a red circle here. The first mile and the last mile requests are created every 3 minutes, and as many requests can be paired together in this setting, in this case, we obtain up to 20% gain over existing approach, especially for higher capacity, that is capacity of 10. To conclude, we have provided an approach to efficiently perform ride sharing for high capacity vehicles. The current approach is myopic in nature, that is, it considers only currently available requests. In future, the work can be further extended to consider future demand to improve the assignments. Thank you.
Thank you very much, Meghna. So we have some time for questions. Let's remember that this is the best paper award in application for ICAPS. Mauro. This is good for a healthy style of life.
Yeah, sorry, Paolo. I was curious about the way in which you created the different zones. So you showed 2 techniques. Is one of them working significantly better than the other? And since I think they are done offline, do you think that by calculating the zones online, you can improve further the performance of your approach?
Okay, yes, so there is a difference between the service rate which we obtained using the different clustering methods. So the grid-based clustering, because the travel time approximation is very bad, so that performs really bad. But for the hierarchical clustering also online, we construct the zones offline, but we do construct zones of different sizes. And online, we decide that which zone size to use based on the number of requests which are grouped together. But yes, if the zones can be created dynamically at runtime, it can further improve the matching.
Thank you, Meghna. Still a question? When you make this kind of abstraction, you have different way to, it is this kind of partition, or you have overlapping zones, and you have different way in which you can improve or can be worse the performance of the online part.
So we don't have overlapping zones, so these zones are complete, means that each zone is different area of the city, but yeah, we obtain the means we observe that when we use with the hierarchical clustering, when the zones are when the travel time is properly estimated within the zones, the performance is better. So yeah, using better zones is always going to improve the performance.
Thank you very much, Meghna. Thank you very much for your talk. Yeah. So the second talk is given by Anil Sharma, and it is about reinforcement learning for efficient target tracking.
Okay.
We have some time more. Could you restart so that
Yes, I will restart. Is this okay? Hello? Hello? Yeah. So in this talk, I will be talking about my work, reinforcement learning-based querying in camera networks for efficient target tracking. So as we know that camera networks are becoming ubiquitous and are used for various visual analytics applications. For example, consider traffic flow analysis, where the task is to track a vehicle across multiple cameras which are deployed across multiple intersections to estimate the journey time of vehicles for different road segments. Another potential application is monitoring and surveillance, where the task is to track a person across multiple cameras for surveillance indoors. So for target tracking in a camera network, we are given with n camera streams, and the task is to determine the target's position for all times in all cameras. So let us say we are given with a network of 3 cameras, and we are also given with the initial position of the target at the starting frame. So the position of the target is Cx, y, where C is the camera index, and xy is a spatial location of the target, that is the bounding box in the camera C. So we are given with the initial position of the target, and the task is to estimate the position of the target for all subsequent time frames in all the cameras. So like as we are doing, as the target is moving across all the cameras, we have to estimate its position. So there are many existing approaches for tracking in camera networks, and they are following a 2-step approach. The first step is SCT, which is single camera tracking. The second step is ICT, which is inter-camera tracking. So we are given with the tracklets of the target in all individual cameras. And in the first step, we are linking these tracklets using visual data association to form the single camera trajectory of the targets in all individual cameras. In the second step, we are linking these single camera trajectories of the targets to form the multi-camera trajectories, and it is also done using visual data association. So often the visual data association is a re-identification based method. And if we zoom into this part, so what is happening is, so let's say we are given with the target's trajectory in camera 1. Let's say at time t1, the target exits this camera field of view. Then a typical tracking algorithm will start querying all the cameras of the camera network to look for the presence of the target. Let's say at time t1 plus t dash, the target is found in camera 2. Then the previous trajectory of the target is linked with the new detections. The same is followed when the target exits camera 2 at time t2 to resolve future handovers. So the vision community has largely focused on visual data association, and they have significantly improved its performance. But they have ignored the querying aspect, which results in redundant querying even during ICT, and it also impacts the tracking performance. For example, like if there is a small false alarm in data association, then the error will propagate to the whole trajectory. So for efficient target tracking, we need to answer few questions. For example, like how often do we need to query? And which camera shall we query? So that we can reduce the number of queries and we can efficiently track the target. So for motivation, consider an illustrative scenario with a conservative case of 5 cameras, having 3 persons per camera. 1 minute of this data set at 10 FPS will generate around 9,000 person bounding boxes. And if we use the solution described in the previous slide, there will be around 9,000 re-identification queries made to the camera network. And if this re-identification based method has 1% false alarm, then there will be 90 false alarms in a minute. These solutions are also querying all the times, even during camera transitions, which is not even required. So to understand the challenges in tracking a target in camera networks, let us consider this figure, which is the top view of Duke MTMC dataset, which contains 8 cameras deployed in Duke University campus. These 8 colored polygons shows the field of view of 8 cameras of the camera network. And the key challenges are like, so first challenge is that like, we always don't know the camera network topology. That means we don't know which cameras are linked to which one. The second challenge is that there are blind spots between cameras. So that means like these field of views are non-overlapping, and the tracking algorithm should be vigilant of the target's position even during these blind spots. The third key challenge is that they generate a very large amount of data, and which increases the computational complexity of the tracking task like with the number of targets. So there are various baseline approaches that are used in existing methods for querying in-camera networks. The first one is a naive approach, in which when the target exits in camera 1 at, let's say, time t1, then all the cameras are queried exhaustively at all the times. The second approach is named neighbor, where instead of exhaustively querying all the cameras, we are querying only the neighboring cameras of the camera from where the target is exiting. So in this approach, we are always assuming that the camera network topology is available. The third approach is named Gaussian, in which we are estimating the transition time distribution of the targets from a training set. And for the testing time, we will sample a transition time from the estimated distribution, for which we will not query any camera. After the transition time expires, we will query only the neighboring cameras to look for the presence of the target. So our problem statement is, let's say we have the trajectory of the target in camera CI. So now we have to identify which is the next location of the target. So to predict the next location, we first need to decide whether we should query a camera or not to query, because we don't know whether the target is transitioning between cameras or is in a camera. Let's say at time 5, we will not query any camera. CX represents that no camera is queried. The same is at time 6. And let's say after time tau, we decide to query a camera. Now if we have decided to query a camera, the question is in which camera the target is most likely to be present. So we need to select a camera where the target should be present. So let's say we select camera CJ. We'll make a re-identification query to the selected camera to find its spatial location, and then we will continue with the tracking process. Please note that these camera transitions are time varying and are dependent on the target's characteristics, for example, its speed and its destination. We are learning the probabilities of these camera transitions, and we have formulated it using a Markov decision process, in which we are learning a policy to answer these two questions. So a Markov decision process is a tuple of 5 elements. The first element is a state vector, which contains the last seen location of the target. For example, let's say there are 4 cameras in the camera network, and the target is present in camera 2. We will extract the frame, we will divide it into regions, and we will identify the regions where the target is present. Then C, R is the last seen location of the target. The second element of the state vector is the camera history, which is the history of cameras queried by the policy. The third component of the state vector is the time count after when the target has disappeared from the camera C. The action space is encoded by an n+1 dimension vector, where n is the number of cameras. For example, if the policy has decided to query camera 2, then the corresponding action is selected. If the policy decides to not query any camera, then n+1 action is selected, which is represented by Cx. The reward function is defined for each state, irrespective of the action taken. If the target is found present in state ST, a positive reward is given, otherwise a negative reward is given. To learn the policy, we have used value-based methods, in which we have used state action value functions, Qs, A, which represents the estimate of the average future reward for taking action A in state S. The optimal Q functions are learned using well-known method Q learning, and an optimal policy selects an action from the learned Q functions using this equation. So this figure shows the complete architecture of our method. So in which from the multi-camera stream, we will extract the last seen location of the target, and then history and time vector are initialized, and then using Q learning, we will select a camera. If the selected camera is not CX, we will make a re-identification query to the camera network to find whether the target is present or not present. If the target is found present, we will update the last seen location. If the target is not present, the history and time vector are accordingly updated. This process is repeated until the video sequence ends, and it will give us the complete trajectory of the target. To evaluate the performance, we have used an LPR MCT dataset, which contains 4 sub-datasets. Set 1 and set 2 are captured from footpath and an indoor building, set 3 from indoor office building, and set 4 from outdoor parking lot. We have created a training and testing set by randomly selecting half of the people in the training set and remaining half in the testing set. The tracking performance is evaluated using MCTA metric, which is a product of 3 scores. F1 score signifies the detection performance. Within camera score signifies the stability of the tracking algorithm in single camera field of view. Cross camera score signifies the stability of the tracking performance during handovers. To evaluate camera selection performance, we have used accuracy, precision, and recall, where P is the predicted sequence of cameras, G is the ground truth sequence of cameras, and CX represents that no camera is queried by the policy. To quantify the computational performance, we have used metric F, which gives us the count of number of spurious queries made to the camera network by the policy. For example, to compute these metrics, let's say we have 2 sequences of cameras. Sequence G is the ground truth sequence of cameras. Sequence P is the predicted sequence of cameras. The colored circles show a camera index. X represents that the target is transitioning during this time. To compute accuracy, we will count out of all the time steps, how many of them are matching. To compute precision, we will see out of all predicted cameras, how many are correct. And to compute recall from all ground truth cameras, we will see how many of them are recalled correctly. So to compute number of spurious frames queried, so we will see how many of the queries are wrong. For example, in the first one, the target was transitioning, but a camera is queried. This is spurious. In the second one, a wrong camera is queried. This is also spurious. So in this example case, there are 4 spurious re-identification queries. So camera selection performance is shown in 2 cases. The case 1 is inter-camera tracking, where cameras are selected only during camera handovers. And we have compared our policy's performance with the baseline methods that I have described earlier, and using accuracy, precision, and recall. I am showing results only for 2 datasets, and in these datasets, our policy is outperforming other approaches in terms of accuracy, precision, and recall. For the case 2, the cameras are selected not only during camera handovers, but also during single camera field of views. And the comparison is shown for all the 4 datasets. And in these cases also, the policy is outperforming other methods. So as expected, this exhaustive and neighbor approach are having perfect recall, but they have poor precision, because a large number of re-identification queries are made to the camera network. These figures shows the computational performance of our policy and its comparison with baseline methods. The y-axis is the number of frames queried by the different methods. And we can see that our policy is making a very few number of queries as compared to the other methods. So even very recent methods in computer vision community are using exhaustive methods to search the target in multiple cameras. We have seen the same case with other datasets as well. This figure shows the qualitative performance of our policy for 2 targets, P1 and P2. For each target, there are 2 sequences of cameras. Above the black line is the ground truth sequence of cameras, and below the black line is the selected sequence of cameras by the policy. The color index shows the camera index of the network. So we can see that like most of the camera handovers are recovered by the policy. So there are few cases where the trajectory is delayed. So for example, in the brown color in the target 1, so the target is delayed a little bit, and it depends on the speed of the target, like how much delay will be there. So these 2 tables shows the tracking performance and its comparison with the state-of-the-art tracking methods on an LPR MCT dataset. This table shows the MCTS scores for case 1, that is inter-camera tracking. That table shows MCTS scores for case 2, that is both single camera tracking and inter-camera tracking. The first few methods are the state-of-the-art methods, and then the other one says that like, so we are using our RL-based policy to select cameras, and then we have simulated errors to have a complete re-identification pipeline. We have simulated errors from 0 to 20%. And in that table, we can see that even at 20% errors in re-identification, our policy is giving better tracking as compared to the other state-of-the-art methods. In this table, at 15% error, we are having comparable performance with the other state-of-the-art methods. This video shows a small demo of the camera selections using our policy. So there are 4 camera feeds and a simulated top view. The initial location of the target is highlighted, and a red bounding box is shown to the target which we are tracking. So when a policy selects a camera, that camera feed is brightened. If the policy says that the target is present in none of the cameras, then all the feeds will be dark. So now the target is nowhere and the policy is not querying any camera. The target has appeared in some other camera. So there is a specific case here. I'm not able to see the. Okay, so. Now the target has disappeared from the field of view and it will take some time to reappear in the camera network. Now the policy will have some problem in re-identifying the target. So, okay, it has stopped. Okay, maybe. Okay, now the policy is selecting like cameras randomly, but it will be able to recover like where the target is present. Okay, so it has recovered the target. So that means if it is making wrong camera selections, it is recovering its errors. So thank you for listening to my talk. And if you want to access the code and the paper PDF, these are the links. Thank you.
Questions? Yeah.
Thanks for the talk. With all the hype around deep learning, I am wondering whether you thought about directly reasoning about the pixels in the image with deep reinforcement learning, for instance.
So basically, like we have not used the entire image. So this is like the result that I've shown is using a value-based, the value-based reinforcement learning, in which the values are stored in a table. So we have extended this approach using neural networks, but even in that, we are not using images. So what we have done is, we have like extracted the regions where the target is present. Like basically, we are using only the bounding box location where the target is present. So I think so have I answered your question?
Yes, but okay, I understood that. I was just wondering why well, is there a good reason not for directly reasoning about the raw pixels of the image using deep reinforcement learning instead of decomposing in a bounding box identification?
Yeah.
And then
basically the thing is like, so we have not done any feature engineering here, but so we see that like, so we don't need that much larger state space. So that's why we are like only using the bounding box location.
So this is using MDP formulation of this problem. I'm curious how this applies to completely different camera formulations. For example, you have an entirely different structure,
yes,
with entirely different orientations. How transferable is the training process or learning process for this?
So these results are on on a small data set which has like 4 cameras. So our extension, we have shown it on like larger data sets. So for example, like this data set which has 8 cameras, it has like both overlapping, non-overlapping field of views, and it contains around 2,800 targets. So and yes, the approach is scalable to the different camera networks.
Okay.
Thank you. So let's thank the speaker again for this talk. Thank you. So next presentation, next talk. Wow. You should turn it off.
Sorry.
Next presentation will be given by Wayne Chi, and it will be about optimizing parameters for uncertain execution and rescheduling robustness. Okay, thank you.
That was a little small. Okay. Hi, so my name is Wayne. Thank you all for being here today. I'm going to talk to you about some of the work that we've been doing for the Mars 2020 onboard scheduler. So, last November, Mars 2020 officially announced that Jezero Crater would be the landing site. And in a little over a year, in next July, Mars 2020 is officially expected to launch. So it's a pretty exciting time to be working on the project. And this right here is an image of Jezero Crater. So for those of you that don't know, Mars 2020 is NASA's next planetary rover project, the previous of which was MSL, also known as Curiosity. Now, Curiosity has had its series of challenges, and one of its challenges is its really inability to deal with a variety of execution uncertainty challenges. So how MSL usually created a plan was scientists and rover operators, et cetera, would get together. They would formulate a plan with fixed time points for each activity, and then they would send that up to the rover, and then the rover would execute those activities. Now, the problem with that is, in order to ensure that all the activity is executed, they would make them over-conservative, and then inevitably, when the rover executed them, they would finish early. And now we have this time, energy, data volume left over on the table that we want to be able to gain back. And so one of the goals with the Mars 2020 onboard scheduler is to be able to recoup those additional resources from prior onboard execution. So on the bottom right on that graph, it's actually a case study done by one of our group members, where for MSL, it was Param Pills, where the blue is the amount of extra time left over, and the gray bars are the amount of extra energy converted to time. And so you can see that for each of these columns, which is a single sol, which is a Martian day, you can see there's actually a couple of hours left over for each sol that we could really be gaining back if we were able to maybe add other optional activities or shift activities forward. And so the Mars 2020 onboard scheduler, or onboard planner, is a single-shot, non-backtracking scheduler that schedules in priority first order and then never moves or removes an activity after it's been placed in a schedule. Activities aren't really preempted. And then it doesn't really do any search except for when considering valid start time intervals or when generating and scheduling preheats, wake-ups and shutdowns, and maintenances. Now, some of you might be wondering, well, that seems like a really simple algorithm. And the answer is yes, it is a really simple algorithm. And the reason for that is because the Mars 2020 rover is extremely computationally limited. To give you an idea, the Mars 2020 rover has a processor that has a grand total of a whopping 200 megahertz. So it's really not a lot of power that we have on board, and it also has to be shared with other tasks on board, such as autonomous driving. And so as a result, the scheduler has to be quite simple in order to operate on board the rover. Now, as you all know, the input parameters set to any sort of scheduler can determine how effective the scheduler is. The issue is even more exacerbated because we have such a simple scheduler. So our main goal with this paper was to basically offload that computational power onto the ground and generate an input parameter set and then upload that to the rover so that the scheduler will be able to perform more efficiently. So one of the first parameters that we came across that we wanted to manipulate was activity priority, which is really the order in which the scheduler considers activity for scheduling. And you can easily imagine how, depending on what order you consider activities, right, you may be able to not schedule them or be able to schedule all of them. And this is a very simple and trivial example. But as I talked about before, one of the main goals of the Mars 2020 onboard scheduler was to be able to get back unexpected resources from execution uncertainty. So that means the scheduler is actually going to reinvoke and reschedule on board the rover. And so each time the scheduler reinvokes, it actually has to deal with a different problem set, right? Different activities will have already finished executing or finished committing to execution. As a result, the scheduler and that priority set has to be able to handle all of that as well. But of course, we also have to deal with actual execution uncertainty as well, right? Activities will end early, and maybe the scheduler will reinvoke and move things forward, or activities will end late, and suddenly an activity no longer fits in the schedule. And the same priority set that we generate on the ground has to be able to handle all of these different situations. Another parameter set that we wanted to consider was preferred time. So each activity is given a preferred time where the scheduler will try to place the activity as close to its preferred time as possible without violating any constraints. And on the top left, you can see how if the activities were given the same preferred time and perhaps they had some resource conflict, no matter the order in which the scheduler considered them, only one of them would be able to be scheduled. But if we were to separate their preferred time on the bottom, you would be able to easily schedule both of them, no matter their scheduling priority. And so you can see how preferred time can be a tool for us to allow more activities to be able to execute, right? And again, this same parameter set is generated on the ground, so we won't, so when we send out the rover, it has to be able to handle the execution uncertainty and the multiple scheduler reimplications as well. So how do we do that? Well, we do an approach we call parameter search. And this is because we're searching for parameters and we're quite unoriginal computer scientists. So this approach is analogous to squeaky wheel optimization. So we're given an input set of activities, constraints, and input parameters. And while squeaky wheel normally constructs one single schedule, what we do instead is we're going to construct a Monte Carlo of execution simulations. So in each of these rows is a Monte Carlo, and in each of these rows is an execution simulation. So the scheduler will actually be re-invoked multiple times, and for each of the Monte Carlos, we're actually going to give them different activity duration variances. So activities will end at different times. As a result, the scheduler will re-invoke at different times. And as a result, different activities will execute in different orders, perhaps, and maybe different activities will be dropped, right? So then we're going to aggregate the resulting score from all these schedules, and we're going to analyze all of these schedules and then reparameterize and repeat this process over and over again until eventually we reach a satisfactory schedule or we run out of time. So our scoring, right? Our scoring is very simple. We're primarily concerned with being able to execute all of our activities. We have some secondary metrics like having a higher handover state of charge, which is really the energy that we have left over for the next plan, or distance from preferred time. Operators can give an input preferred time, and if we can click closer to that, then that's better for our scoring as well. But the reason it's so simple is because the Mars 2020 team has made it very clear that they really are only concerned with one thing, right? They really mainly just want all the activities to be executed, and if we can do that, that's great. All these other features are just gravy on top. So how do we change the parameters? Well, we start off with some simple methods, right? There is the intuitive max step, right? Where if an activity isn't executed, you just promote it to the top of the priorities list, and then the activity will have to be able to execute it, or it's just a faulty plan and it will never be able to succeed, right? Then we have a stochastic step method because max step might promote it much higher than it's needed to be, or it might encounter some cycles, so you add some sort of stochasticity in order to avoid that. But we actually have a lot more information. We actually have all the activity attributes, their constraints, and so as a result, we wanted to be able to use that. So this method, the intersect method, we tried to analyze an activity's start time windows and try to analyze an activity's resource pitch, which are their unit resources, in order to determine where we can place the activity and try to guide the activity's priority placement that way. But we actually have more information. As I talked about, we actually do this Monte Carlo of execution simulations. So we can dive deep into that, right? We can take a look at all the execution simulations that we have. And while we're mainly concerned with the final executed schedule, you can imagine that if an activity failed to schedule in one of the intermediate schedules, it signifies that it's perhaps brittle, right? Perhaps in another parameter set it would have dropped. So we want to increase its priority in order to make sure that it will be able to execute. Perhaps we just got lucky in all of the Monte Carlos. And you can also imagine that we have, let's say, 100 or thousands of Monte Carlos. It's very different if an activity fails to execute in just one of the Monte Carlos versus if it failed to execute in all 1,000. And so we apply a weight and change priorities based off of that as well. So the previous were all preferred time methods, or were all priority methods. And now I'm going to be talking about some of the preferred time methods we have for manipulating parameters. So the first method is similar to the intersect method, where we're analyzing activity attributes, right? So we know that, again, we know the activity start time windows, and we know that the activity has certain unit resources, right? So instead of changing activity's priority, when it fails in the Monte Carlos, we're going to take a look at activities that have higher priorities than it and try to shift it away from where that activity that failed could be potentially placed. We also have multiple iterations of our squeaky wheel algorithm, right? So we can actually take a look at where the activity was perhaps scheduled with a different parameter set. Because you can imagine that even though it failed in the current parameter set, perhaps before it was able to be scheduled somewhere with a different parameter set. And so as a result, we can analyze that and take a look at the history of the activities placements and try to shift other activities away from where we know the activity can be placed. And lastly, we have a portfolio method. Right? And this is really because the previous methods we've described all are very different, and they all have their strengths and weaknesses. And also because we don't actually know what plans will look like for Mars 2020 yet. We have some idea, and I'll talk a little bit about that later. But we want to make sure that our technique is robust to whatever they can throw at us, right? And so we do a simple portfolio. Right now, it's definitely just a uniform distribution of all the methods we previously talked about, and we recognize that we can learn a better distribution, right? There's a lot of work on that. And so we did some empirical evaluation. These are soul types, which is what I was talking about before. These are best available data for what we think Mars 2020 plans might look like in the future. And these plans aren't simple. They aren't just serial, right? They have start time windows, dependencies, resource conflicts, et cetera. But as I said before, we're not 100% sure on what plans will look like in the future. And so as a result, we tried to constrain them in various ways for what we intuitively think plans might be different. So for instance, we tried to constrain the activity duration variance to simulate scenarios where activities have high duration variances. We tried to decrease the activity start time window constraints to simulate plans where their activities are much more constrained. And we also tried to vary incoming stated charge because we have a good estimate of what might come in for each day, but that estimate is not always true, right? And we compared it against a few static algorithms as well. So we have random assignment, which is random. And then we have latest start time, which is very analogous to earliest deadline, except it's the earliest latest start time for each activity. And then we had a human expert, someone with actual MSL experience, lay out the plans as they might have laid them out for MSL. And we assigned the priorities of each activity so that the earlier the fixed time that they get it, the higher the priority. So in our results, we saw that parameter search outperformed all the static methods across the board. We also see here that depending on the different input parameters, or the different plan variations, the different parameter search methods actually perform differently. So for instance, the preferred time methods performed well when there was high activity duration variance, but they didn't perform well when the start time windows were constrained. And this makes sense because when the start time window is constrained, there might not be enough room for the preferred time method to move activities around. And so we consolidated all of the plans together and all of our data together and tested our portfolio method out. And you actually see that our portfolio method, despite being so simple, actually outperforms all the other methods. You can see that it has a higher score overall over here, and it also actually converges faster as well. In the top right, you can actually see that it actually increases the handover state of charge as well, but this one we're less clear about because as you might expect, more activities should lead to less energy, right? But perhaps we're guessing that activities may have been scheduled in more efficient places with this method, and as a result, lower the amount of energy usage. So for our future work, we definitely want to apply learning to our portfolio. As I said before, we currently do a uniform distribution, and it's very simple. We also want to be able to do a better analysis of our activities. Like I talked about before, we have all this information about activities, and we tried to do it with the Intersect method, but there is definitely more detailed analysis that can be done. For example, there's a lot of work on STNs. This is just one example of one paper. And we want to be able to use that in order to, for example, analyze which activities are brittle in our plan, and then try to shift the activities of those shift the priorities of those activities instead. We also want to do some work on our Monte Carlo. So our Monte Carlo eats up a lot of time, right? And one of the things that we can do is we can try to decrease the Monte Carlo samples required to reach an acceptable confidence. And as a result, we can perhaps speed up our search and spend more time searching in the parameter space rather than in the execution variation space. And lastly, there was work done previously, actually at this conference. So if any of you attended his talk yesterday, he did some work that was very similar, but instead of doing a Monte Carlo, Michael did a probabilistic analysis instead, and he was able to find lower bounds for things. So in conclusion, we showed that parameter search for Mars 2020 was a challenging search problem. We formulated our approach as an offline approach analogous to squeaky optimization. We showcased that all of our parameter search methods are able to outperform the static methods, and then we showed that even our very simple portfolio method was able to outperform across all of our plan variations. Thank you.
Okay, time for question.
Why is the state of charge handover?
Anna, wait, you need to be recorded. No, you have to speak here.
So why is the state of charge handover such an important artifact?
Why is the handover state of charge important?
Yeah.
So the higher the handover state of charge, the more energy you have for the next plan, right? So after one plan ends, you just basically hand over to the next plan. And so the more state of charge you have.
But what if you end up with having too much? What do you do with the rest? Is there a contingency that you're looking at to say you have a contingent plan that you're stored that you could execute if you have extra energy? Why are you building up all of the extra handover?
Right, so I don't talk about it in this presentation, but we actually have a variety of activities that we can use. So we have what we call optional activities. And if we have extra energy, for instance, they might try to jam in more optional activities for the scheduler to put in, right?
So you're sure that's going to happen on board? Are
What
you
do you
sure
mean?
that it's going to actually happen on board during the mission?
What is going to happen on board?
The possibility of contingent plans actually being executed. You are making a design assumption about certain things.
Yes.
Is it the baseline?
Yes. Okay. So I don't know what you mean by contingent plans.
I mean,
right?
what are you going to do with the extra SOCs? What is the question?
Right. So there are a variety of different activities, actually, that we can add to any single plan. So like Steve was trying to mention, we have something known as switch groups, which are really 3 activities that are jumbled together. They're the same activity, but they're of varying durations, right? And depending on how much energy you have, the scheduler will autonomously choose one of the activity that consumes the most energy. And so you can see how if there's more energy, it'll be beneficial in that way. I don't know if that answered your question as well.
We can talk offline.
Okay. Okay. There's also a paper in PlanRob and IWIPS that talks about that, if you're interested.
Still some questions? No, so we thank Wayne, I thank the speaker. Okay. This is the journal track paper. It will be presented by Andrew Branch. Front delineation and tracking with multiple underwater vehicles. If we will, oh great.
Okay. So, like you said, I'm Andrew Branch from the Jet Propulsion Laboratory. And today I'm going to be talking about our work that was published in the Journal of Field Robotics late last year on front delineation and tracking with multiple underwater vehicles. This work was done in collaboration with the California Institute of Technology, Woods Hole Oceanographic Institution, the Monterey Bay Aquarium Research Institute, and Remote Sensing Solutions. So a quick outline of this talk. First, I'll be talking about the motivation of why we're interested in doing this. Second, cover some related works, and then discuss our algorithms for doing this front delineation and tracking. Then finally finish up with a field program that we performed in Monterey Bay as a proof of concept test. So as you could guess, we're interested in tracking ocean fronts, where an ocean front is the boundary between two distinct bodies of water. In this image, you see here in the bottom left part, this colder water that's upwelling from the deep ocean that's a bit further offshore. And close to the shore, you see this warmer surface water that's been sitting on the surface for quite a while, so it's been heated up by the sun. And then we see this ocean front in the middle, which is where these two bodies of water meet. So there's really two main properties of ocean fronts that are important for our work. One is that, as you can see here, it's a gradient between the two bodies of water, so it's not a very sharp change. Often it's more gradual change. And two, these ocean fronts are driven by currents and tidal tides and the bathymetry, the seafloor, the topology of the seafloor. So they move quite a lot. So as they're moving, we want to stay in contact with them. And our goal is to run repeated transects across an ocean front, where a transect is just an underwater vehicle traveling in one direction for some amount of time. And we want to do that as many times as possible across this front. In this case, we're using temperature, but really any oceanographic measure is useful. Salinity or chlorophyll are two other options. Now, traditional methods would use scientists with running fixed transects with humans in the loop. So they send some transect to the vehicle, it performs it, they get the data back, they look at it, say, okay, we didn't intersect the front, or we did, but we were a little bit off, so let's adjust what we've done and send it back to the vehicle and continue on. So our motivation is to be able to improve the science data by using near real-time data processing in ocean models. We can do that by shortening up these transects so that they're only covering the interests of the area of interest for the scientists. So we have less data on either side, and we can cross the front more frequently to observe it evolving over time better. This also allows us to do things like track ocean fronts in areas where there is very little communication and you can't get enough data back to be able to do this with a human in the loop. An example of this would be under ice. So there's a number of related works that have done oceanfront tracking before, most of them using a single vehicle approach. However, here we are using a multiple vehicle approach. So before we can actually track the fronts, we need to be able to detect them. And to do that, we've developed this lateral gradient front detection system. So the idea is to detect a change in the water property, which signifies a front, over one single transect. So here we have the raw data from a single transect. And these vehicles are performing what's called yo-yos. So they're going from the surface or near the surface down to, in this case, 40 meters, and then back to the surface, back to 40 meters, and just repeat that along the entire transect. So we can take this data and interpolate it. And here we use linear interpolation. Then we can smooth that data to get rid of, or to reduce any kind of erroneous data. And then finally, we can differentiate it. So now we have this plot showing how that water property changes over the course of that transect. Now, scientists tend to not be interested in the full water column. They tend to be interested in a fairly small range of depths. In this case, we're looking at the 10 to 15 meter range. So we take this data here, and we sum it at each time step over the range that the scientists are interested in, giving us a plot that looks something like this. So here, over the time, which represents the time along the transect, can also be used to infer the distance along the transect that the vehicle is at. We have how the water property is changing at that point. So we can set thresholds. In this case, we're using 1 and 1.2 standard deviations of this data set here. And then that is denoted by this dotted line. And then any time that we cross over that dotted line and then come back under that dotted line, we can declare a front, because we're interested in going into the area of high gradient and then leaving the area of high gradient, indicating that we've moved into the other body of water. So here we can see that we have maybe 1, 2, 3, 4, 5 locations where that's actually happened in this one transect. Then we need to somehow select one of these fronts. In this case, we're selecting the widest front, not necessarily the strongest front, because if the front is spread out over a longer region, then the change in water property will be less significant at any individual time step. So we use the longest front, which is this one. So after we have some method of being able to detect fronts, we have developed a method to actually track them. And to do this, we use multiple vehicles which are running in near parallel transects. So we see a figure over here showing this. And this is a very idealized figure in that there are these three vehicles that are running perfectly parallel transects. In reality, that's not going to happen. But they're going to run a transect, and then they'll run their front detection algorithm and come up with some point on their transect where they think they've crossed a front, or they might not have seen a front at all. And then we can use just linear regression to estimate a linear front, which we see here in red, and then we can command the vehicles back across that front perpendicular to it, like these three dotted lines. So like I said, the chance of these vehicles staying in these perfect transects all next to each other is basically 0. So we've developed the algorithm such that it doesn't really matter if the vehicles get out of sync. So when the vehicle is estimating a new front, it'll use the front detections from the other vehicles for some set amount of time. We don't want to use really old detections because that's going to be out of date and the front has probably moved since then. But if we use a sufficiently short time window to do that front detection, we can operate these vehicles out of sync. So here we have a bit more detailed example of exactly how this is done. So assume that the vehicles are starting up here at some given location, and we command them along some minimum transect length. We have this minimum transect length because scientists aren't interested in very short transects. That doesn't give them sufficient data to make any conclusions. So they want transects of some minimum length. And then after that, we run the front detection algorithm. This is not being run constantly on the vehicle. This is actually off-board the vehicle in our particular case. So we only run this periodically. And then either the vehicle is going to detect a front or it's not going to detect a front. If it doesn't detect a front, it just continues along its transect, continues to look for that front. If it does detect a front, like in these two examples, it's actually still most likely going to continue along that transect, because not only do we want a minimum distance length, we do also want a minimum distance past the estimated, or past the detected front. This is once again because the scientists want some data on either side of the front to get an idea of what's going on in each of those bodies of water, as well as the intersection of those two bodies. One other note here is that it is possible to detect a stronger front later in the transect. So in this particular example in the middle, we detected a front in this first leg. However, in this next leg, we detected an even better front. That's probably more indicative of what we're looking for. So in that case, we just throw away this original front detection and use the new one. Then we can use just linear regression to estimate a linear front and command the vehicles perpendicular to it. And then this process will just repeat until the vehicles are recalled. So to test this, we went in May of 2017, we went to Monterey Bay, and we had 3 different vehicles deployed in Monterey Bay. We had some IVER AUVs here up at the top, and those were provided by the Woods Hole Oceanographic Institution. So those are fairly fast vehicles at 2 to 4 knots, but they only have daily endurance, so about 12 hours. So they need to be deployed daily off of the Shauna Ray, which is a research vessel in Monterey Bay. Next, we had the LR AUVs, which are a little bit slower at 1 knot. However, they have multi-week endurance. So they can stay out for a couple weeks, then are recovered, and it's all commanded remotely through satellites. And then finally, we have the Sea Glider, which is provided by California Institute of Technology, which is even slower than that at about half a knot. However, it has multi-month endurance. It can stay out, in some cases, up to 6 months at a time. And you can see over here on the map exactly where those vehicles were located when we were commanding them. The IVERs were quite close to shore because they had to be deployed daily. The LRAV is a little bit further away, and then the Sea Glider is way down here. So, one more note. In this case, in this presentation, we're not going to be discussing the LRAV data because unfortunately there were some operational issues with the LRAV, which are discussed a little bit in the paper. However, we're going to skip over those for today. So first, we have the IVER AUVs. And to give you some idea of how far these vehicles are actually traveling, we set the minimum transect distance length to 2.5 kilometers. And if no front's detected, it would continue 2 kilometers more before running the front detection algorithm again. So this plot over here is the data that we collected with 2 vehicles over 2 different days. It is a bit obtuse when you first look at it, but up here at the top, we have the start locations of the vehicles on day 1 over here and on day 2 over here. And then we have the front detections drawn. You may note that there are 2 front detections when you would only expect there to be, or 2, sorry, these are the front estimations that are drawn. You would only expect there to be 1 for each recommanding. However, unfortunately, there were some issues with recommanding the vehicles, so they were commanded slightly incorrectly compared to what they should have been. So in blue here, so this guy, we have an example of a correct, or how the vehicle is actually commanded relative to the estimated front. So you see the vehicles came here south, and then this front was estimated, and then they're running perpendicular to that front. Now, in this very short example, we weren't able to get tons of data, but you can generally see that there's warmer water up at the bottom and the cooler water at the bottom, or warmer water at the top and cooler water at the bottom, and the front detections in between. We also over here developed a metric to actually try to quantify how well we're tracking the front. That's quite difficult to do because of how kind of nebulous a front is defined. There's really no clear definition. But we have one metric tracking a fixed transect method that the scientists might use, so having just the vehicles running on a single transect, and then our front tracking metric. Unfortunately, today I don't have time to actually go into how that's calculated, but it's all covered in the paper. As you can see, the front tracking metric was able to more closely estimate where the front was going to be and then command itself appropriately. Next, we have the Sea Glider data. Unfortunately, we only had 1 Sea Glider, so we couldn't do front orientation. We could only do front position. So here we see that we selected an orientation that was where the scientists thought that orientation of that front would be. And then the Sea Glider was commanded on a transect across it. So we see a number of transects that were actually completed, these 6 up here. And actually, on the next slide, it's a bit easier to see exactly what's happening. So this is a side view of the vehicle's data. And then each transect is separated by these white bars. So here on the first transect, we see that we got this front detection where it switches from this cooler water to the warmer water. And then on this transect, that's when the vehicle turned around and went back across the front, where we see the same front, just slightly weaker. And then at this point, the front had kind of dissipated or moved away from the region that we were interested in. And then later in the week, it came back, and we saw this very strong front detection. Also, down here, we will note that the front tracking metric in this experiment actually performed worse than the fixed transect method. We believe that this is due to the region that we are operating in. It was a very dynamic region. The front was moves quite quickly, closer to and away from the shore. And the Sea Gliders are very slow vehicles. One of these transects took approximately a day, maybe a day and a half, depending on the exact transect. So by that time, the front had moved quite far away from where our estimate was. So in this case, a faster vehicle at this location would be much better. So for our future work, the kind of obvious thing to do is more deployments and testing. This is very clearly a proof of concept test where we've developed a system that can do this kind of work. However, we want to do more work where we have more direct comparisons between a fixed transect method and a front tracking method. We also want to add in more capabilities to distinguish between the different ocean fronts that we see. Often you will see multiple ocean fronts that are very close to each other. So you will need to distinguish between going from warmer water to colder water, or colder water to warmer water, sharper fronts versus more gradual fronts. So the scientists can target exactly what they actually want to sample. We want to do some onboard implementation of the front tracking. Like I said previously, all this work was done off-board, and commands were sent to the vehicle over a satellite network. We want to incorporate a nonlinear front model, which has been done previously with a different front tracking method, but with using a nonlinear front model. And finally, two last notes. One, incorporating an ocean circulation model into operations. So being able to initially target the vehicles using an ocean model to help the scientists say, okay, this is where we want to send the vehicles to initialize this front tracking method. And then finally, coordinating beyond different types of vehicles to fully utilize the available assets that the scientists are using. So finally, in conclusion, we've developed a method of autonomous tracking of ocean fronts using multiple vehicles. We've demonstrated a proof of concept in Monterey Bay with a number of vehicles. And we've introduced a quantitative metric to actually evaluate the performance of front tracking algorithms. Thank you.
Questions? Yeah, kind of course. After working so long time, maybe.
So one way in which you can augment what you're doing, you're looking only at temperature.
Yes.
In the bay, what really matters is multiple variables that you want to look at. Nitrate, salinity for sure. And if you go further north, east towards Santa Cruz, the energy of the front is much stronger.
Yes, this is.
Right? So this is dissipating because the energy from the canyon essentially is pulling it down. What you want to be doing is to look further up north.
Yes.
And there is where you want to look at the three parameters you want to, and then correlate them.
Yeah, so this is Santa Cruz right here.
Right.
So this is where we were focusing the IVR deployments, but it is a very well taken point that temperature itself isn't enough. That it's more complicated.
So what was the contribution of models in this paper, or did you not do it?
So in this paper, yes, we didn't have any ocean models run
specifically. With a seed. If you had run ROMs there and actually use that as a seed, you could have placed your vehicles in a much more strategic manner.
Exactly.
But you didn't do that?
No, not here.
Okay. That's old work. You should have just followed that and done it.
Yeah.
Because that's been done.
Well, yes, so that's a good point. So we did something like that in 2016 where we were taking ROMs and looking for fronts in it to target. However, we did not do it in conjunction with this work in the same deployment.
And are the vehicles actually communicating when they're up at the surface or no?
They are only communicating with the shore, and then the shore does all the computation and sends just waypoints back to the vehicles.
So basically, they pop up every couple of kilometers. You send the data back to shore. There's somebody synthesizing everything together. That's when you're able to do the regression and say, here's approximately where the front is.
Correct.
Right? And how are you making sure you're...
Yes.
How are you making sure that you're not running into a filament?
Into what?
Into a filament, that it's not a real front.
I mean...
You can't, right?
Yes, so the idea is that we're going to go far enough past where we think we've detected a front that if you were to hit the actual front, then you would be able to detect it and it would be stronger.
Okay. Your idea of moving an onboard implementation, which are the main issues and which are the main advantages?
So the main issues are, one, vehicle communication. Having the vehicles communicate directly to each other could be problematic. And it's feasible, but it's just more difficult and more expensive. The main advantages, I think, are that if the vehicle cannot communicate to the shore to send data back and for the shore to talk back to it. So if the vehicles are under ice or in communication deficient environment, then they're not going to have that option and they will need to talk directly to each other.
Thank you.